Hello everyone, I'm Zijiao, a senior AI researcher at Tencent Games. I'm thrilled to be here today to talk to you about GoSkinning, which is an innovative and efficient skinning tool. This AI-based skinning tool is automated and can greatly improve skinning efficiency. My presentation will be divided into 3 parts. Part 1 will give the background of GoSkinning. Part 2 will introduce GoSkinning and its details. And Part 3 will discuss its applications. Let me start by introducing the background of GoSkinning. In video games, characters play an important role. Different game styles require different characters, which is reflected in the garments and accessories. So the creation of the character is crucial to game development. There are 3 main steps in the 3D character creation process. During the first step, the modeler creates a 3D model based on the prototype design. In the second step, the animator creates a skeleton for the character and binds the vertices to the joints. Finally, the third step is animation production, where the animator creates animations for character. However, the traditional skinning process is currently done entirely by hand, which is both time-consuming and expensive. Before we discuss how to solve these issues, let's explore the theory of skeletal animation. 3D character is made up of mesh and skeleton. The movement of the vertices is driven by the skeleton using the LBS algorithm. In this animation, the vertex is influenced by the 2 nearest joints, and its position is directly linked to the position of the joints. As shown in the center below, you can see the skin weight metric, which is the output of the skinning process. So automatic skinning is about automatically calculating the skin weight metric. The columns of the metric represents the number of vertices, while the rows represents the number of associated skeletal joints. Next, let's review the challenges involved in implementing auto-skinning. There are 3 main challenges. First, characters have various geometries and topologies, leading to different meshes and skeletons with varying complexity levels. Accordingly, we've divided the meshes into 2 categories, that is, simple and complex meshes, based on the difficulty of skinning. Secondly, due to its complexity, it's not trivial to effectively construct a neural network to accurately predict the skin width. Finally, neural networks inevitably incur corner cases, which need to take good care of to improve the automation. Let's see how GoSkinning is tackling these challenges. Let's start with the GoSkinning video show.
The mesh and skeleton are unbound currently. Select entire mesh vertices and their associated skeletal joints. Start the auto-skinning process. It takes about 10 seconds to 2 minutes, depending on the complexity of the mesh and skeleton. The skinning process is now complete, and the animation runs perfectly.
As you can see, it's so convenient, very easy to use. Okay, let's move on. GoSkinning is a data-driven skinning tool, incorporates many deep learning methods. This tool aims to fully automate skinning and minimize manual work. As shown in the figure, users only need to provide the mesh and the skeleton, and the tool can automatically calculate the skin weight. Currently, GoSkinning is almost workload-free for simple meshes and takes only a few hours for complex meshes. In contrast, manual skinning takes a day for simple meshes and 1 to 3 days for complex meshes, making it labor-intensive. GoSkinning is 6 times more efficient than manual work. In the following slides, I will discuss how GoSkinning has achieved this. Here is an overview of GoSkinning, which involves 3 processing steps. The first step is full skinning, where the full skinning neural network infers skin weight for all vertices of a calculus mesh with its associated joints. However, this neural network has some limitations and can cause some artifacts, such as mesh skeleton binding errors. To address these issues, we developed the partial skinning neural network, which allows users to fix underperforming parts by rebinding partial vertices and joints, which are all selected by users. Despite the strength of these neural networks, corner cases such as intersection errors can still occur. So in the third step, we included many auxiliary utilities, such as geometrical processing tools to resolve these corner cases. Based on this framework, our approach can perform well in most situations. Now let's dig into it. First, let me introduce the full skinning neural network. The full skinning neural network aims to skin the entire mesh in an end-to-end manner. Given the entire mesh and its associated skeletal hierarchy in the raster pose, the full skinning neural network can automatically skin the entire calculus mesh in a single inference that results in high-quality deformations. We developed a neural network that accurately models the skinning process. It uses a graph neural network, which can handle unstructured data, such as characters with varying numbers of vertices and joints. It takes 3 inputs: vertex attributes, skeleton attributes, and bone chain attributes. The outputs are skin weights. In addition, we carefully designed multiple modules to precisely extract diverse and impactful features. The vertex feature representation module extracts local features, global features, and labeling features of the vertex. The joint feature representation module extracts both local and labeling joint features. The relationship representation module extracts the relationship between vertices and joints. Lastly, the bone chain feature representation module extracts the bone chain features for the vertices. Okay, let's dig into these modules. First, I will discuss the vertex feature representation module, which aims to learn local and global features for each vertex, as well as aggregate neighboring features. The input consists of 2 parts. The first part consists of the k-nearest joint features for each vertex, including joint positions and the distance between the vertex and the associated joints. The second part includes vertex features such as position and vertex normal. We constructed 3 graphs, including mesh graph, KN graph, and the clustering graph, to aggregate neighboring features. The mesh graph remains static and follows the mesh topology, while the KN graph adapts dynamically based on the k-nearest labels of the vertex features. Additionally, the clustering graph relies on the clustering results of the vertex feature. Then we use an edge convolution module to aggregate adjacent vertex features. In addition, we use the MLP structure to extract global and local information such as mesh style, body part association, and so on. And finally, we obtained comprehensive features of each vertex. The purpose of this section is to facilitate information exchange between vertices and joints by applying joint-to-vertex convolution and vertex-to-joint convolution respectively. Since the mesh graph and scalar graph are unbalanced, with thousands of vertices in the mesh but only a few joints in the skeleton. To handle this type of heterogeneous data, we use the vertex-to-joint convolution to transform the vertex features into joint feature space, and the joint-to-vertex convolution to transform the joint features into vertex feature space. For more details, please refer to the paper below. Through this module, we can effectively exchange information between vertices and joints. The Bunchen feature representation module is the final component of the full skinning neural network. It takes the features of the k-nearest Bunchens as input, which are measured by the geodesic distance between the vertex and the Bunchens. The features include the joint positions on the Bunchen and the geodesic distance from the vertex to the Bunchen. The outputs are embedded Bunchen features for vertices, which is encoded by the MLP structure. It was noting that vertices are often affected by multiple joints within the same Bunchen, highlighting the importance of the Bunchen attribute. Next, let's talk about the loss function. Before we dive into loss function, we need to introduce the output of the model. Since each character has a different number of skeleton joints and different topology, it can be tricky to fix the output. So in our method, we first get the k-nearest joints for each vertex and output a vector with a fixed dimension. The widest n represents the number of vertices, and the head k is associated with the k-nearest joint. This way, we get the answer and fix the output dimension. Now, let's talk about our loss function, which has 3 terms. The first term is the Kerr divergence loss. We consider the output weight map as a label distribution, where the weight vector is a selection of k-nearest joints with different probabilities. We calculate the loss between the two distributions with Kerr divergence. The second term is the smoothness loss, which aims to promote even distribution of predicted skin weight by constraining the gradient of skin weights between adjacent vertices on the mesh. The next term on the right side is the deformation loss, which is used to encourage predicted mesh to deform realistically, similar to the ground truth. By incorporating these 3 terms, the model not only ensures consistency of skin weights with ground truth, but also guarantees the smoothness and the release of mesh deformation. Next, let's examine its results. We connected over 3,400 simple meshes from gameful pieces and split them into 3,300 training samples and 160 test samples. To evaluate the neural network, we used an L1 distant heat map that highlights prediction errors in red and accurate predictions in white. The results indicate our model's predictions are highly accurate and with small errors. We also created a complex mesh dataset, and the results below show that even on complex meshes, the effect is also good, with an average of L1 distance of is 0.21, which is slightly higher than that of simple meshes. This is because complex meshes has a variety of meshes and skeletons, making it more difficult to learn. Here are the results in more applications, including the game PUBG, QQ Speed, Crossfire Mobile, and QQ Dance. Most of them can achieve good results, except for a few complex meshes that have made some corner cases, such as multi-layered traces in game QQ Speed and QQ Dance. So there are still some limitations. The first limitation is the binding errors caused by the complexity of the mesh and skeletons. On the other hand, there are some artifacts on skeletons because of the ambiguities on skin weight assigned by the artist. This ambiguity decreases the accuracy of the neural network. To address these issues, we propose another novel method, the partial skinning neural network. Basically, the partial skinning neural network is to fix any underperforming parts remained by full skinning neural network. In addition, in this module, we allow users to select a portion of vertices and the corresponding joints arbitrarily, which means fewer mistakes and more control over the binding style. The figure shows how it works. Users select the vertices and joints you want to work with, and the partial skinning neural network predicts the skin weight for the selected vertices. So to achieve the goal and ensure the generalization ability of the neural network, more attention should be paid to local features and the relationship between selected vertices and joints in terms of network design. The architecture of a partial skinning neural network is mainly composed of iteratively applied edge convolution and intermodule. The edge convolution module operates on mesh graph and skeleton graph to extract vertex features and joint features, respectively. The intermodule operates between mesh graph and skeleton graph to get the relationship. And the square distance module calculates the square distance between joint and vertex features to obtain final skin weight. The neural network takes the positions of selected vertices and joints as inputs and produces skin weights for selected vertices as outputs. And the loss function is the Kerr divergence. In contrast to complex architecture of the full skinning neural network, partial skinning neural network enhances the local features of vertices and joints and the relative relations, in showing the generalization ability of the neural network. So the partial skinning neural network is simpler than the full skinning neural network. The construction of dataset includes 3 steps. Step 1, segment the character meshes based on mesh connectivity. Step 2, sample vertices from each segment. Step 3, obtain the associated skeletal joints for the sampled vertices. The data visualization is shown in the figure below, where partial vertices are colored brown and the partial joints are colored green. To ensure the generalization ability of the neural network, we selected various of types of meshes, totaling over 20,000 meshes. Let's take a look at the effectiveness of the partial skinning neural network, as demonstrated in the figure on the left. These binding errors in both cases were effectively resolved by the partial skinning neural network. Moreover, as indicated in the figure on the right, users can customize the mesh and skeleton binding style to eliminate ambiguity, resulting in the removal of most of the artifacts on the skirts. Moving on the third part, let's dive into the topic of auxiliary utilities. As many of you may already know, tackling all problems at once in supervised learning can be quite challenging. There will always be corner cases, and GoSkinning is no exception. After performing full and partial skinning process, some issues still remain, as shown in the figure. We have identified 4 types of errors, namely intersection error, deformation error, fracture error, and gap error. To reduce the need for manual adjustments, we have developed a suite of geometrical processing tools to address these issues. First up is the intersection correction tool. It's a really handy tool that detects corresponding vertices in overlapping regions and ensures the weights are consistent. Next, we have the collinear optimization tool. With this tool, we can detect collinear vertices and constrain the skin weight. Next, we have the boundary weight constraint tool. This tool is essential for keeping the skin weight of vertices on the boundary as consistent as possible. Throughout the process we have just introduced, which consists of full skinning neural network, a partial skinning neural network, and auxiliary utilities, GoSkinning is able to solve most of the problems and greatly improve the efficiency of skinning. Let's have a look at its applications. Here is a demonstration of GoSkinning.
The mesh and skeleton are unbound currently. To begin, you'll need to select the entire mesh and skeleton. Next, start the auto-skinning process. It takes about 10 seconds to 2 minutes, depending on the complexity of the mesh and skeleton. The skinning process is complete. Most of the vertices are skinned perfectly, but there are still some artifacts, such as binding errors. Select certain parts of the vertices that are underperforming, and use the partial skinning neural network to rebind them. Once the partial skinning process is complete, your character mesh should be able to deform correctly.
It's so efficient, only 2 minutes for the skinning process. Here are the final results. The 2 videos above show the effects of Game for Peace and Tiandao. The first 2 videos show that the prediction results are identical to the ground truth. The next 2 videos show the results of QQ Dance. The animation is remarkably realistic. Until now, within Tencent games, over 12 games are using the GoSkinning tool. The tool has proven to be about 6 times more efficient than manual work, resulting in savings of millions of dollars per year for some games. Okay, that's all. Thanks for your time.